So it is my pleasure now to introduce our second team. Team 2 is representing Tulane University. Everyone please give a round of applause for Isabella Kulstad, Sal Chavez, and Thomas Coutreau, who will be speaking on interferons, a biomathematical approach to modeling innate immunity.
Hi, so my name is Thomas Coutreau. I'm presenting along with Saul and Isabella on interferons. So let's get started. So first, I'm just going to explain like what interferons are and what they do. So basically, how the process is when a virus goes and infects a cell, this then causes the viral cell to release both viral particles and interferons. And so then these particles then go interact with other cells surrounding the patient zero cell, as seen in the diagram. And so the interferons basically cause the cell to become protected and not allow like the virus to get into it. And the virus can go infect other cells as well. And so basically the goal of the interferon is to basically kind of fence in and like prevent the virus from spreading throughout the rest of the body. So we're gonna go and talk a little bit more about this. So the two main like actors in this system is interferons and virions, and they are very much opposite but equal kind of reactions, which we're going to see. Is interferons go and protect cells while virions go and infect cells. They both do this in a kind of radial pathway surrounding from that cell that it's generating from the middle. With interferons, they eventually cause the cell to undergo apoptosis, which is not really a good thing. But they don't get infected and doesn't allow infection to spread. And the virions, when they go and infect the cell, the virus eventually causes the cell to eventually cease function too. So the interferons are good, but not really in a huge sense. You don't want all cells getting protected from the interferons, because then they all will eventually undergo apoptosis and die. And also the one difference is only the infected virus cells produce both the virus particles and interferon particles. And so today we're going to kind of be looking at like this interaction, which kind of leads to our main question. What is the ideal interferon virus diffusion ratio necessary to quell the spread of infection?
So this leads to our ODE. So as we mentioned in the diagrams, we have a few parameters and 3 different populations we're going to be talking about. We're going to have our S population, which is our susceptible population at time t, our I population, which is our infected population at time t, and our P population, which is our protected population at time t. And this all equals our N value, our entire population of cells at time t. When we can add them together, we can get N of t, so our population of cells at time t, equals our susceptible population, our infected population, and our protected population. And then therefore, when we take the derivative of all of these, we can see that when that population of cells is changing, it's going to equal the change in susceptible population, change in infected, and change in protected. And since we're working within an ODE system and we're limiting ourselves to the amount of cells we have, this population is never going to change. So you can actually see this in some of our ODE equations. So as I had mentioned, kind of going off the diagram that Thomas made, we have 3 different populations: our susceptible, our infected, and our protected. And kind of going off of the TIV, the SIR models, these models are not connected. So once a cell is infected, it doesn't eventually become protected or become recovered. It simply that does not exit the system. So we have 2 different contact rates. The first one is beta, which is our contact for infected rates. And we have alpha, which is our contact rate for protection. And you can see this in our differential model. So the change in our susceptible population is when our infected population is going to take away from the suscepted, creating that subtraction, that beta times the infected population at time t times the susceptible population at time t. And then we're going to head and also subtract our alpha population, our protected population. So subtracting by our protected population, which is alpha times the infected population at time t times the susceptible population at time t. And then kind of from that big susceptible change model, we can see that when we take the derivative of our infected population, that's going to be our beta value, which is our contact rate again, the infected population at time t, and the susceptible population at time t. And similarly, along the same vein, our protected population at time t is going to equal alpha, which is our contact rate again, the infected population at time t, sure you're sick of hearing me say that, and our suscepted population at time t. So this is our ODE model, but of course that's incomplete. And two of the things that we were curious about is one, what is the relationship between the interferon and the virus rates? And two, when does the model end? So to start off, the interrelationship, we took a quick ratio right here, the ratio between the different differentiated taking at I of t and the differential taken at P of t. So that's our rate of new infections under our rate of new protections, lambda protect over lambda infect. And this, using our contact rates, is just alpha over beta. So when we compare these two, we have the derivative of P at t equals alpha over beta, the derivative of I at t. When we take a quick integral, we can see that the relationship between the virus and interferon rates is P of t equals A over alpha over beta times the infected population at time t. And then another thing we were curious about is, okay, we have this model. When does it end? What values is it giving us? So when we set these derivatives equal to 0, both for the I of t population and the P of t population, we set them equal to each other. And given that alpha and beta are both constant rates, we notice that the only time that this model will end is when I of t equals 0 or when S of t equals 0. So this means that either there is no infected population in the first place, or there's no susceptible population because the entire model has been infected. So this is obviously limited because, as we know, when we get infected, we have natural immunity systems, our innate immunity that comes from these interferons, which actually don't end up playing a huge role in this ODE model. Instead of when we get an infection just ceasing to exist or not even having an infection in the first place, we have some innate immunity factors, and that's where our net logo model comes in.
So the first model we created was kind of a full-scale particle containing model, and this model was really good. The cells are, each patch is a cell, and then there's two kinds of turtles, the interferons and the viral turtles. But the main issue that we had with this model is, as you can see on the right, there's a lot of parameters that go into making this model. And so when we were trying to study it, it was becoming very difficult to actually be able to tell and like changing things. So we needed to kind of come up with a simpler model to be able to actually run some tests on it. So that's why we went to.
So after simplification, our model became the particle-free model. Rather than dealing with individual viruses and interferons moving around, this model focuses on the interactions between cells. So every tick, an infected cell chooses a cell in its surroundings and tries to infect it. The distance at which this cell is located is determined by a normal distribution. Similarly, infected cells will also try to protect a number of cells around it. The diffusion rate variables let us determine the shape of our binomial distribution for each action, and the lambda variable determines the ratio of effective actions. It represents how many protection attempts occur for every single infection attempt. Finally, there are two more important parameters that do not change throughout the experiment, but have to be calculated for a specific disease first. This model is said to have an infection per cell every tick. That means that the tick duration is said to be the time between each infection. In this case, is 2 hours. And the lifespan is the amount of time a cell can be infected before apoptosis. Because in this case, is 24 hours. After 12 ticks, each cell will apoptose, meaning it will no longer either infect or protect any cells around it. For this experiment, we decided to keep the virus diffusion at a constant rate of 0.05. This value allowed for fast but not uncontrolled spread that resembles a real viral infection. And for the actual runs, we decided to keep the values of lambda and interferon diffusion rate bounded. Values outside these boundaries were found irrelevant since they were either too low, that there was no control at all of the infection, or too high that the infection was almost immediately suppressed. The experiment was run at every possible combination within these boundaries, which yielded this surface. This surface plot shows the relationship between lambda, the interferon diffusion rate, and the fraction of cells remaining untouched by either virus or the interferons. Yellow areas represent complete suppression of the infection. Green areas represent cases where the infection is controlled, but significant damage has been done. And finally, blue areas represent uncontrolled infection. We can quickly draw the following conclusions. Either really low lambda or really low diffusion rate values provide almost no protection against infection. When the interferon diffusion rate is at least as high as the virus diffusion rate, meaning 0.05, a lambda value of 4 ensures complete protection, And finally, interferon diffusion rate becomes more significant for smaller values of lambda. For really high lambda values, even having an interferon diffusion rate to virus diffusion rate ratio of less than 1 is enough to suppress infection. Another one of our expectations for this experiment was to find a Goldilocks zone regarding interferon diffusion rates. We fear that a high diffusion value will be counterproductive, as the goal of interference to fence in the infection becomes harder if cells that are too far dispersed get protected rather than close ones. Our findings show that this does in fact not occur, and as interferon diffusion increases, so does the amount of cells that remain untouched. It is worth noting that for extremely high values of both lambda and interferon diffusion rate, the value does drop drastically when interferon diffusion rate increases, but this is not because the infection is being allowed to spread, but it's because the majority of the cells are just being protected for no reason.
Okay, so some limitations and areas of continued interest. So first, cells are presented in a lattice structure and not really organ specific. So like our model is kind of just like a more vague general model. And like also there are a lot of other factors and influences going into like the body, like fighting off infection, which we really do not show in the model, including viruses have their own defenses against to stop interferons, which we just don't really go into. And this is only, our model only was for like a single type of interferon and not a lot of different types, because there are many different kinds of interferons. We basically just modeled the one basic one. Areas of continued interest, interferons exist in multiple varieties and interact with immune cells. So expanding the model would be to show those kinds of interactions. Two would be a cytokine storm and other fever-inducing interferon effects. Three, adapt model to be disease specific. So our models kind of doesn't really code for a specific virus, but we could tailor it and make it more specific to count to be for a specific virus, and also introduce artificial immunity.
So we would like to take some time to thank everyone for first of all listening and for contributing to our project, specifically the program lead, Dr. Michael Levine, our project mentor, Maya Mims, and some of the following teams, that from Georgia Tech, Georgia State University, and Georgia State/Clemson University right there. You guys were fantastic in giving us ideas, giving us feedback, and engaging and being really interested in developing our final project. We'd also like to thank the Southeast Center for Mathematics and Biology for their both financial and educational support during this program. Without SCMB's support, none of this experience would have been possible. We are eternally thankful. Thank you all so much for listening, and we are open for any questions you may have.
I will provide audio for the various clapping emojis I see in the chat. Wonderful talk. Thank you, folks. I will open the floor to any questions and comments.
Hey, thanks for that presentation, guys. I had a question about your net logo model. It looked like in your original iteration versus the simplified one, the pattern for the interferon spreading through the cells was pretty different. Could you comment on why they would move differently?
Oh, yeah, I can take that. So actually, in both cases, they like kind of spread radially. So yeah, but the second image shows like a really strange behavior. It's kind of lines like moving around. This is actually simply because this specific experiment, like those parameters, this run was made with the parameters shown on the picture. It's like probably one of the most volatiles I've found. Like it was kind of a 50-50 chance what was going to happen. Sometimes the entire screen was filled. Sometimes like it barely spread at all. Maybe I should have chosen a different one for the picture, but you know, it was just like I kind of just chose randoms. I kind of like how it looked and chose it. But yeah, this was really volatile. The behavior of this specific parameter situation just it's like really strange. Maybe that is something we should like look into what happens at these ratios. But in most cases, it also like it's either spreads radially or it just doesn't spread at all.
So I think at one point in the presentation, you said something I think that was really, really helpful, which is you said the point of interferon is to fence in infection. But I don't think you showed us a simulation where that happens. Do you have any images of a simulation where interferon does its job, where it did the darn thing and it fenced in the infection? I think we'd like to, you know, that's like the That's like, that's the zone that that interferon is hoping to find itself in, right? And then I guess my follow-up question to that is, does your model then suggest this, would you be able to pinpoint this Goldilocks zone of diffusion ratios that then could go be measured and compared to what's actually observed?
So as you see, there is no Goldilocks zone, like it didn't exist. If we make the interference diffusion rate super high and the lambda like relatively high, between like at least higher than 4, we will see a decrease in the amount of untouched cells. But that is not because the infection is escaping. That is because like so many cells are getting protected so far away from the infection that of course the untouched cells are going to start decreasing.
Not sure if this is exactly a question, but just something that I thought was cool. Like seeing how like after like along with the what you guys did as well with interferons and virions, how you could tie in the immune response as well. Like eventually they kind of start coming in, like the neutrophils, like macrophages, killer T cells, stuff like that. Like, you know, the whole army's kind of coming in now, depending on how bad this you know, virus or infection is. So
Yeah, it's super cool. And a lot of those processes, those macrophages, some of those like natural killer cells are covered within different interferons. So we focus only on interferon alpha, but there's several other interferons with several other Greek letters tied to them that activate those more, which is why I really like this model, because it gives us the opportunity to add those on eventually and kind of increase this to be more of a full-scale realistic model.
that's really cool. This has a lot of potential, this simulation right here.
Okay, I just added a slide with one of our particle full models that actually does stop the infection.
Okay.
Should be like just at the end. I don't think we have any like images of a particle free. We just didn't really do it. We just kind of like set it straight into the behavior space.
Yeah. So wait. So let me give Team 2 a lot of credit. They took this very complex particle-free model that had many parameters, very high dimensional model, and were able to make some very clever modeling assumptions that reduced the model down to one where the turtles, the turtle element of the full model was basically summarized in a statistically rigorous way. And it results in a very fast, effective model that you're seeing here now. Wow.
I had another question for the team. You guys talked about sort of varying varying the binomial distributions you use to sort of represent the infection rates and like the rates at which sort of these particles are spreading. Can you talk a little bit more about that choice and like the importance of using sort of like a like using that like probability distribution in your model?
The binomial distribution doesn't really have to do with the rate at which cells are being infected or protected, more with than the range. So it determines how close are the cells that are going to be either infected or protected. And by having the interference having a slightly higher range, then we can like achieve that goal of trying to fence in the infection rather than just like coexisting with it.
Okay, thank you. That makes a lot of sense.
It also did help us to kind of figure out what parameters we should be using for our study, because again, like we didn't go with a specific disease in mind, so we didn't have an idea of what exactly we wanted to do for like that lambda variable or that interferon rate. So using normal distribution allowed us to say, hey, some of these were the interferons, which I believe are the blue patches, and are protecting so far away, aren't going to be valuable and aren't really going to represent the system that we're trying to represent. So it allowed us to kind of narrow our values down a little bit, refine our parameter study, and thus generate more relevant results.